Well, good morning, everyone. Thanks for being in so early. Today, more PyOpenCL and PyCUDA. Actually, more PyOpenCL, OpenCL. What's the story? Well, first of all, I thought one thing to get you woken up in the morning. Let's do this. Wait. Is a piece of code. Oh no! Yes, are you all super excited? But no need to worry, we've seen this piece of code before. It's the same thing as last time. So I'm just showing this to demonstrate to you. There's all this stuff that we've been handling in this brief introduction, brief overview to OpenCL. There's something that says buffer, there's this command queue, something apparently with the context of the program, then we get something else and something else yet down here, and we don't really know what these objects are. NumPy is an array package for Python, separate from PyOpenCL. Matt mentioned that as a way of transporting data from. Yes, exactly. Or it used to be numerical Python, and then software stuff happened. Now it's NumPy. Okay. Right. Okay. So yes. Point is, we've been dealing with this stuff, and you know, it says command queue. It's kind of there's an intuition of what it might be, but let's talk about it in a tiny bit more detail of what's going on. So, in summary, it's going to be a tour of the toy store. So, toy store has two parts. If you recall this graph from this diagram from last time, there's the host side, has its own memory, and then there are all the devices, each with their own memory. And the way to talk to the host side of OpenCL is through the runtime, as it's called, up here. So if you do that in C, you would include a header called CL/CL.h, and then link to a library called libopencl.so, or whatever it is on Windows. And in Python, across all platforms, all you do is import PyOpenCL as CL. On the device side, on the other hand, as in to talk to these guys, to tell them what to do, to tell them the program that they're supposed to execute, you talk to them in a dialect of C99 that we've seen. If you look back at the program, we've already done a bit of that. So there's here something that sort of looks like C, except it has these funky little annotations in it. Right, so let's get to know all this stuff a little bit better. How we're going to go about that? Well, first I'm going to talk about the runtime a little bit, then about the device language, and finally I'll discuss a few details of OpenCL implementations that are around. In particular, I'll talk about NVIDIA's, I'll talk about Apple's, and I'll talk about AMD. Okay, get right to it. There. A whole UML diagram. I don't like UML. Still a good overview of what's going on. So, like a spider here in the middle, sits the context. In order to get a context, you need a device, and in order to get a device, you need a platform. Once you have a context, you can make a command queue. The command queue can give you events. You can make memory objects. You can have all this image and sound stuff we're not going to talk about. You can also create programs, and programs give you credits. That might be a bit much to remember, and it's all these words there. At least what this tells you the multiplicities. There's mostly just one context, but, and all this other stuff dangles from it. There can be multiple. I'll show you this picture again. You'll have a little bit more attention so you know what this is. Right. Start at the beginning. All starts, well, you have to start somewhere, right? In order to start talking to OpenCL, you need to know, well, the goal is to talk to one of these compute devices, right? And before you can get to a device, it turns out you have to pick a platform. And one of the selling points of OpenCL is that there can be multiple. They come as just files that are shared libraries that are found by this libopencl.so that we've seen. That is actually not the implementation. That is just what's called the ICD loader. ICD for installable client driver. And how does this thing find the implementations? Well, it looks in this directory, etc OpenCL vendors, some named ICD, for the name of a shared library where it finds the actual implementation and dynamically loads that. And so there can be multiple. And installing them is as easy as dropping a file into one directory and pointing the ICD loader to where to find the file. Then platforms themselves provide groups. Oops, I should probably stand in front of the slide. Platforms themselves provide groups of devices. Next thing to talk about is a device. Device can be pretty much anything that can sort of be shoehorned into this grid programming model. So it might be CPU, might be CPU is some. I said the definition of a device is a processor die with an interface to off-chip memory. So each individual processor that has an individual memory bus would be reflected into CL as its own compute device. Or a GPU, obviously has its own memory binding off of it. Also, CL has facilities, for example, to talk to cell broadband engines. Not that that's particularly relevant anymore, but all of this is supposed to be aggregated into the same way of talking to compute devices. And ideally, the same code will generally work, even though it will probably not work fast. But how to make it work fast across a broad range of devices, that's the topic of next time. Main purpose of these platforms that we talked about is to give you a list of devices that's contained within it. So great. Then you know what device you're talking to. Next thing you create is a context. Yay, isn't it great? More nouns. How do you create a context? Well, you give the context. So this is the first bit where we see some PyOpenCL based code. You create a context. This is if you're unfamiliar with Python, this is a constructor call. Commonly classes are named with capital letters. So that's how you. It looks like a function call, but if this here is a class name, that's actually just a constructor call. So you make an object called context. And you give it a bunch of devices. That's actually the first thing that's interesting. Because a context can span multiple devices. That'll become important later on. So give it a device, or you can prescribe a device type. Or in OpenCL, in PyOpenCL, if you just want to get going, just give me some device, I don't care. Then you just say that. Because, well, in order to get a device, you have to do all this enumeration that I'll show you in just a moment. And I said all of that. And as we saw in the diagram, you need a context to do pretty much anything in CL. You need to allocate memory, to create programs, to do all this stuff. Command queues and to execute those. And they're attached to everything. Right. Yet another noun is the command queue. What's the command queue's purpose? Command queue is sort of the mediator between the host side and the device side. As I said, the two run asynchronously from each other. So when you issue GPU commands, they don't actually get executed right when you issue them. They get put on top of this queue. This command queue thing is the program representation of this queue. So if you want to do something with this queue, say wait for it to drain, or see are there still commands pending. This is the object that we talk about. In CUDA, there's a direct correspondence to this called stream. Like the word command queue better. Right, and the host can put all kinds of stuff onto this queue. You include your computations, you include your memory transfers, you include your synchronization primitives all into this queue. You can have more than one per device, such that as you submit work, the device can pick from all the queues that are active on it at any given time, so that you can have parallel things going on, so that if one queue isn't filling up the machine, the other is. And by default, a queue sequentializes all the stuff that you submit to it, so that you submit a memory transfer, you submit a program execution, you submit a memory transfer out, as we said last time already, you don't have to worry about them overlapping because that's exactly what the queue is for. That said, unless you turn it off. So when you create a command queue for which you need a context and a device, so command queues are device specific. They only go to one device. You can also specify a bunch of properties. And one of these properties is if you want out of order execution, at which point calling the whole thing a command queue becomes kind of a but we'll see on the next slide, maybe 2 slides onward, why that is a useful thing to do. In addition, since command queues are also about timing somehow, this is the point where you can enable profiling and ask the device to collect timing data on the commands it runs, so that you can later get out how long something took and what the exact timing relationship when you execute it and when it's actually had it. Yeah. Absolutely, yeah. See, one device, multiple queues. That's absolutely no problem. That's actually very useful. That's right. I was like that. Right. Okay. So, key points to remember: one device per queue, but multiple queues per device. That's the multiplicity. And you can switch into out of order. You can do profiling. And once you have a command queue, you're pretty much all set. That's all the setup work. All the stuff that you don't have to do in CUDA because it just picks a device for you automatically. It creates a context for you automatically. But then when you want to switch context in CUDA, switch devices, that gets kind of fun. So a little bit more upfront work for choice. That's how I. So how does this work? Well, in PyOpenCL, you just ask for the platforms that it finds, and you get a list back. You can take the first one. You can print the vendor of that. Then you can get the devices in that platform and pick the first one. Print the name of the device that you get out. Create a context on it from that one device. And last but not least, just create a command queue on it. Now, if you look at that and think, I didn't have to do all of that in my CUDA program, then just use that version down here. If you don't care, by default this is interactive and it'll prompt you. I want this device. I want that device. Okay. That's the neat thing is I think I can do this right now on my laptop. So in front of you, if it'll work. This here is the exact same code that we saw, and then it'll just do some simple vector addition. Run it, and it indeed found the AMD implementation on an Intel processor, and whatever it did yielded 0 error. Yay. Okay. So that was just setup stuff. You care about that when you create your working environment and think about where you want to run your code. Now, every time that you enqueue something in a command queue, it turns out almost all of these things are named cl.enqueue something. Enqueue read buffer, enqueue write buffer, enqueue enqueue range kernel, but you don't see that because it looks more like a kernel call. Hold on, I'll briefly switch to that so you see it. Here where we run the kernel, that's actually also in enqueue. So every time you perform one of these enqueue operations, what happens is you get an event back. What's an event? Event is this kind of just an identifier for the time span that this operation took. In particular, what the event knows is when when something is over. So in order to synchronize the host to what you're doing on the GPU, the event has a method called wait. So that you can just wait for that thing to be done on the GPU. Or if that floats your boat, you can also call and ask, are you done? Are you done yet? Are you done yet? You can also wait on multiple events at the same time so that you can see whatever is done first. Wait on one or multiple. Right. The interesting thing, though, is that not just can you on the host side wait for an event to be done, you can also have members of the queue, things that you enqueued into the command queue, wait for each other. Turns out all these things that you enqueue also take a keyword argument wait for, and that's what you give it. What you feed that here is a list of events.
You can do a whole. You can assemble a whole DAG.
Oops. Thank you for saying DAG. Yes. So as we heard in Professor Scott's lecture yesterday, an important thing in parallel computing is the data dependency. So you might do a bunch of things where you have one stream of code that results in one result, one stream of code that results in another result. Then you combine those, and this gives you the vocabulary to express towards the CL implementation how things depend on each other and what can be run in parallel. And as devices get wider and wider, I imagine that this gets more important. Let me briefly jump back. So this is what this wait for aspect of events is for. So it lets you specify the data dependencies of your operation, and it lets you synchronize different streams of operation. Also, this is where if you do your data dependencies this way, you can safely switch your queue to out of order mode, and that's precisely what this is for. Because otherwise you'd have to manually think, okay, how many different streams of execution do I have, and which one does each one go to? If you switch your queue to out of order mode, you can just submit it all to one, and if you specify your directed acyclic graph of dependencies correctly, then everything will get executed in order. In particular, you can emulate the old behavior of just sequential execution just by having each operation wait for its predecessor in the queue. So this is strictly more general than the old way, if you need it. Yeah? Memory allocations actually happen outside of it. Yeah. Everything that you submit into the queue must have its memory available for its entire execution span. So you must have your memory allocated, then you submit your work, and then you synchronize out, and then you're free to preview. I see what you're saying. That might be useful at some point in the future, but it's not available right now. It would be quite complicated. Right, sure, yes. If you scale this up, and if you do many independent things with that have many things in memory that they work on independently, yes, you can run out of memory. But that's an inbuilt risk of working on computers. Finite size, unfortunately. GPU memory is kind of a little bit more finite than other memory. Right. Okay. So this is what command queues and events let you do. In addition to that, they also let you do profiling, as in obtain very fine-grained timing data. Shouldn't switch yet. If you have profiling enabled in your queue, there's an extra attribute of each event that as soon as it has gotten to each stage, you can query when an event got relative to some global timestamp in nanoseconds. You can query when it got queued, when it actually transferred from the queue to the device queue, and then when execution on the device started and when execution on the device ended. So this is kind of nice. It gives you very precise timing data of what happened when. And you can assemble a timeline out of that. I submitted this way long ago, and it took that long to execute, or it took that long until it actually got executed. So that also gives you an estimate of how long the queue you had that you assembled. Right, profiling works then like that. You can also have artificial events that are not associated to any particular operation. Those are called markers, and they work just like any other. So suppose you issue some library call that's not instrumented, you can still time it just by including a marker at the beginning, including a marker at the end, waiting for that to all have happened, because otherwise you can't meaningfully get the timing data, obviously. So you get an error down here, and then you get the elapsed seconds to. There's a bug here. This should be start event minus start event. So this here gives you timestamps and the difference between the end of the stop event here and the start of the start event. I know it's not quite what it is. That gives you the elapsed seconds between these two markers. And this is not the same time as when the host code passed through here and the host code passed through. Right. On the other hand, if you just want to time a single kernel, it becomes much simpler because you get an event right out of that. You wait for that to happen, and you can just get the difference between start and end for that single kernel. So that's to me that's almost sufficient to get an idea of where I'm spending my time. And also in the lab that we'll have on Friday and Saturday, that'll be the first thing that I'll ask you to do. I'll have a code for you, and your first job will be to figure out where on earth is that thing spending its time, and then you'll go through and try to make it better. So I hope that'll be fun. And as we jumped ahead to this, obviously this data dependency aspect of it, where we can specify a full directed acyclic graph of things going on. And one main thing where I found this directed acyclic graph useful was if I'm communicating between one stream of execution on one GPU and one other stream of execution on another GPU, what happens is I prepare a communication buffer, and the computation in my main program continues. So what happens is kind of dependency-wise, the stuff that goes to the other machine branches off, and it depends on data that's still sitting back here. So it depends on that being ready. I can't start it before then. Yet all the other stuff going on can start in parallel. So, and I had big trouble in the past representing this, and I'm very happy that this directed acyclic graph is now in there. CUDA has something similar. I think that got added in 3.2. Right. So you can branch a stream of execution, and then stuff gets transferred to the next GPU over, and there you do the reverse. You join. So you transform your communication buffer into something that's meaningful to the code, and you integrate that into the main stream of execution by waiting for two different things. And at the other end, it's two different things wait for one thing for one step to be finished. That's a very common application if you do inter-GPU communication. And actually, what I said earlier, as machines get wider and wider, that's actually already a reality in video Fermi devices. You can submit multiple kernels, and if one kernel doesn't manage to fill up the whole machine, then stuff that you might submit in parallel, so say this guy doesn't manage to fill the machine entirely, then this guy and this guy will help. So to my mind, this is an important facility to have, to be able to control. Also, you can include a barrier into a command queue that makes sure that all the stuff that you include before the barrier will finish before execution continues with stuff that's after the barrier. Another important synchronization. All right. So much for dependencies and then synchronization and code execution. Another thing that you commonly deal with is memory. Memory comes in the form of buffers. Buffers kind of unlucky word for that, but you can get used to it. Most interesting thing about buffer, besides being a chunk of device memory that has no type information, is that it's tied to the context. Now remember that a context is not tied to just one single device. It can span many devices. That has an important implication. Namely, if suppose, it is just a chunk of memory, so it sits somewhere in physical memory, and thereby it sits on some device. Now suppose you take that buffer handle and submit it to a kernel that's sitting on another device. What has to happen is that the implementation grabs that data, transfers it to the right device that you're submitting work to, and executes that. And this buffer abstraction provides you complete isolation from where stuff is stored. The assumption is, as long as everything is just happening on one device, and as long as you just need stuff on one device, everything will be efficient. And also, when you need stuff to be transferred to a device, you're issuing that transfer command by using the data somewhere else. So that, if you're not careful, that could be costing you. But on the other hand, then the implementation has all the information. It knows, data needs to go from this device to that device, so it can do the most efficient thing of transferring data from one device to the next. Absolutely, yes. So events, absolutely, yeah. Let me see if I can quickly go. Yeah. Here you see that events aren't in any way attached to devices at all. They're attached to the context, and the context can be attached to multiple devices. So as long as you stay within a context, you're good. There we go. Oops. Oh, it's already full screen. Who knew? Right. Okay. That's one subtlety that's easy to overlook if you just read the standard, but that's actually quite powerful. There's another subtlety that comes in the form of this flags parameter here. It can actually drastically change the meaning of what's going on. Well, okay, you can specify here that you want stuff to be read-only, write-only, or read-write. That's kind of not so exciting. It allows the implementation to take shortcuts and put stuff into read-only memory if it wants to. But aside from that, it's pretty obvious. Here, you can, in addition to that, you can specify alloc, copy, and use host pointer. Those three are actually wildly different from each other and give you wildly differing semantics. There we go. Simplest is copy host pointer. So you give it a numpy array here, and then the last argument that just precedes the contents of the buffer with the contents of the memory that you give it. Simple enough. Use host pointer is a little bit more subtle. You force the implementation to use the memory that you give it as the package store for the data on the device, where caching the contents in device memory is allowed, but every time that something finishes, it gets transferred back to that particular chunk of memory. And that doesn't sound very efficient, so I don't see a good use for it. More interesting, perhaps, is in the last one, alloc host pointer, where the implementation will allocate a pointer that is visible both from device memory space, from device address space, and host address space. So that you get new host memory that's attached to, that's visible at the same time to the device, so that you can do direct communication over the bus. It's a hardware difference. So the question was that what's the difference between use and alloc? Use allows the implementation, so you give it a chunk of memory, And that memory can be regular pageable memory, right? So the implementation doesn't have control over it, and usually the most efficient thing it can do is copy data between device memory and that chunk of memory. For alloc post pointer, the implementation has control over where it puts that. Aside from that, the semantics are the same towards you, but it's a much more efficient thing because the implementation has control of where it puts stuff, and thereby it can put it in non-pageable memory that can be exposed directly over the PCI Express bus to the device, so that when the device writes to it, it goes straight over. Does that answer your question? Any more questions, by the way? You do that by, like I said, just by handing a buffer to that you imagine sits on one device to a kernel that runs on a different device. So the question was, how do you avoid going through host memory when communicating? And the answer is you allocate a buffer, and that buffer is just associated with the context, right? And you transfer your data into there, and you imagine that sits somewhere in some device memory. And suppose you use it on one device once, then you can be fairly certain that it resides on that device. Then you use that same buffer as an argument to a kernel on another device, and you can be fairly certain that it's going to be needed in that device's memory, right? So there's an implicit transfer that has to happen. And that's how you issue those transfers. But aside from that, the implementation is in control of where data in a buffer resides. It's the detail that's hidden from it. It's not very explicit, but I don't see a good need for the extra. Let me also quickly go back. I forgot to mention another consequence of there not being one single physical location to a buffer. Namely, the consequence is you cannot have pointers to this address space that survive beyond the life of one kernel implementation. Because as you go between kernels, the implementation is free to move stuff around, so you have to use indices instead of pointers. Yeah. Right. Right. So, question was, if you're on a cluster, regular MPI cluster with a network by InfiniBand, would you have a context on each node? The answer is you get a choice. I was going to talk about that in the last talk, but why not talk about it now when the opportunity is here? Obviously, if you don't do anything special, you have to create a context on each node. That said, there is a piece of software that is an OpenCL implementation that gives you a single view of all the OpenCL devices in the whole cluster on one machine, so that you can exploit the same vocabulary that OpenCL gives you across the whole machine. Right, exactly. It does the communication for you. It can't scale too terribly well. But where does it know how to allocate the memory? By usage. It's the same way here, right? You just attach a buffer to a context, and if that context spans many devices initially, the implementation has no idea which device the memory actually goes to. Only as soon as you use it, you give the implementation information of where you need that information. Oh, the host node. Yeah, well, I think that by the time you use that cluster spanning thing, I don't think you want to be allocating too much host memory anymore, because you run out. Like all the GPUs on your whole system would need to have much more memory than you do.
Let me ask you a question.
Okay, I'm not advertising, I'm saying it exists, right? You can do it. OpenCL provides the vocabulary. Is it a good idea? Maybe not.
So let me ask you a question about pointers that not survive kernel launch.
Right.
So that means we do things like this. Have one set of kernels that process say computational and set stuff in memory and launch a new set of kernels and use that memory and process it again. But I can't do that.
You can. You just have to use indices to represent where you used to use pointers. And then you can't stick pointers into device memory and expect them to be valid in the expression. But a pointer is usually just an offset from something at the beginning of the buffer.
Oh, so
you store the index relative to the beginning of the buffer rather than the pointer.
Oh, okay. I thought you were. So I think of pointers as what I pass to the kernel for using.
Oh yeah, no.
Call that a pointer called a buffer or something.
Yeah, no, of course. Yeah, the buffer is passed to the kernel as a pointer.
Right.
And those exist, of course. But they exist only from kernel start to kernel end. Okay. Question answered. So the question for everybody was regarding this pointers do not survive kernel launches. Obviously, there are pointers within kernels, right? And these buffers get passed to the kernel as a pointer, and these pointers stay valid within your code. It's just as soon as the kernel ends, the implementation is free to move that buffer just somewhere random, and thereby it could happen that any pointer that you stored, which you can, but it might be invalid after the fact. So if you're doing that, you're skating on data. Right. Okay. Buffers. Right. So we covered all of these things, and you specify memory to give it, or you specify just the size. This host buff in the case of PyOpenCL that you specify there must satisfy something called the Python buffer interface, but you don't care about that. Stuff you can pass to it is, for example, a numpy array or a string. Important. If you're dealing with numpy arrays, it's somehow easy to ignore the memory layout. You know, if you have a matrix, there's always the question: do you go columns first? Do you go rows first? This matters because through this interface, the memory layout is exposed. So you have to be aware which way your matrix is ordered to transfer. And here comes the point we covered just now that has to device as points. You can include reads, write, and so on. And you can also map them into host address space if you do them without Right. Here's a puzzle for you involving buffers and command keys. This here, what do? I get an array of random numbers, pass to a single precision floating point, make a buffer, let's read write and this thing, and I enqueue a write to that buffer. And well, that says it's okay, so there's not much of a puzzle here. Here's something different. I allocate a buffer, I do pretty much the same thing. I feed it an array of random numbers that I cast to the float, and apparently this here crashed. Anyone have an idea why? That's exactly right. So this thing here, the Python interpreter passes this to the enqueue, and as we see here, is blocking equals false. So this function here returns way before the device actually gets around to transferring any data. So before even the device starts transferring, this guy here dies, and the memory might get reused. In any case, it's not valid. So that's why you get a crash. One proper way of doing this is, well, use a blocking transfer so that you know that by the time you get here, the use of this memory is open. So unless you care very much about performance, it's usually wise to default to blocking transfers, and this is what recent versions of PyOpenCL do. Up here, I said that this is okay, Is it really always okay? Not twice. How could it break? Right, yeah. I mean, if this A gets garbage collected before this thing finishes, of course, same thing as in the Crashy. So you have to, if you use asynchronous transfer or non-blocking transfer, then you have to make sure that your data loads long. That's the risk of living in a garbage collected language. That said, you know, PyOpenCL could take that responsibility away from you. I decided against it simply because it would be very, very expensive. Because then I'd have to have lots of state queries. You know, before I garbage collect anything, I'd have to ask them, like, are you done? And I decided not to do that. So this is one remaining risk that I decided was worth going incremental. Right. So we actually want to execute code. How does that go? You construct a program from source and within a context. So again, this goes onto potentially onto many devices. And this here is the source code that we'll talk about in a minute. And you can specify some compiler options, and you can specify what devices you want to be on. You can also create programs from binaries that floats your code. So that if you don't want this could be if you don't want your source code, your device source code to be visible, but for most of you, I imagine it's not. Right, and then you can enqueue this kernel with a certain global and work with grid size and a bunch of arguments, and you can also wait for other stuff. What can these arguments be? Well, they can be a null pointer. They can be numpy size scalars. What is that? So you say numpy in 64 of 15. If you just passed 15, would that work? No, it wouldn't, because at this level, PyOpenCL doesn't know what the type of the argument that OpenCL expects is. So you have to tell it explicitly, these are the sizes of the arguments that I want to pass in. So you need to make sure that these things are cast properly. Or you can pass anything with a buffer interface, and it'll be just literally be that argument and can work in the same situation. You can pass these buffer objects that we discussed. Also, there are images. So if someone tells you about CUDA textures, then the equivalent here is CL images. There are also samplers and local memory that I'm not going to talk about. Now, of course, this whole explicitly sized integer and float business is kind of annoying because it's something that you have to remember to do every single time. So there's a way to avoid that by upfront telling PyOpenCL about the data types of the scalars that it expects, so it'll do the casting for you. So you can avoid, forgetting or casting to the wrong type and getting mysterious crashes. And just, if you're passing non-scalars, just pass none to those first. Right. So those are brief flyover tour of the OpenCL runtime. So I hope this here is a little bit less mysterious. You start a platform, get a list of devices. On a device, create on one or more devices, create a context, and on a device, create a command queue from which you get events. In a context and potentially on multiple devices, you can create a program. Each program can contain multiple kernels, and within the context does not attach to the device in any way. You have both. That's the runtime. Right. Switch gears a little bit. Talk about the device language. Since you've already learned a fair chunk of CUDA, I won't bore you. That's mostly similar to that. So, you have one compared to C99. Compared to C99, you have a couple of gains and a couple of losses. So you have these index getting functions, get local ID that we talked about, and you have memory space qualifiers. I'll show you those in a second. Then one thing that I think is tremendously cool is you have vector data types. I'll tell you why I think they're cool in a minute. then all the math functions, say sine, cosine, all this stuff, are generic. So there's one little bit of OpenCL that pretends to be C++ by overloading, say, sine, so you don't have to type, say, sine f for one single precision floating point. And there's a bunch of synchronization stuff in there, yet recursion and fine-grained malloc are out. And function pointers out. Okay. Right. Yeah.
That it means that it's necessary to for development.
Well, these two are unrelated. You can't have recursive functions because you'd need a stack, and hardware facilities for that are a more recent invention on RPG. They exist now. That's one area. The question is how efficient would recursion be because it would lead to very, very branches. With regard to fine-grained malloc, I imagine that might go away, even though that restriction might also go away. It is gone on CUDA. Yet the question is how efficient is that either? I don't know. I mean, you can pretend to have something like malloc using local atomic operations, but is your question answered? Yeah. That's implementation specific. So, for example, there is stuff on the on AMD for CUDA. I don't know if CUDA GDB works with OpenCL, but I can't imagine no reason why it wouldn't. As far as I know, NVIDIA chose not to expose printf through OpenCL, but AMD does. Right. Okay. So this is basically the overview. Let's go through that very quickly. Here's that dictionary again that I showed you. So now that you know CUDA a little bit better, you'll see that there are quite a few unfortunate choices. For example, in CUDA you say functions are global, and the function in OpenCL you say those are kernels. On the other hand, in OpenCL the memory is called global, where in CUDA it's called device. Here's possibly the most confusing and weird choice that I really don't understand why they did that. What is called shared memory in CUDA is called local memory in OpenCL. Yet there is another kind of memory called private in OpenCL that's called local in CUDA. Worst possible idea. Yet somehow, well, we're going to have to live with it. So just keep something like that stable to the headboard near where you speak. I'm sorry. Right, okay, also textures become images, sync threads become barrier, thread index, it becomes get local ID, block index becomes get group ID, and get local ID. Actually doesn't exist, but it's easy to re-implement. Right, so in that sense there's a direct one-to-one correspondence. And these memory spaces, just to remind you, private is what's called registers in CUDA. Private to a work item, read, write, and usually they're very fast unless they're spilled to memory. And local or shared memory is specific to a group, is read, write, also very fast. Global is the big device memory, and constant memory. I don't know if you've heard about that. Exists too in textures. Key point. It's not part really of OpenCL. Don't focus on just one of these memories. Usually successful algorithms just keep all of that in mind, all of those in mind, and combine the good features of all. Right. Now, as I said, vector data types. Why are those useful? Well, first of all, what do they do? You say load n or double n or what have you, or in u is unsigned in 32, u in 4. So the numbers that are allowed for n are 1, 2, 3, 4, 8, and 16. No others? Just 12. And you can get to the components by saying dot s and then indexing 0, 1, 2, a, b, c, d, e, f, or also by exploiting get that. You can access them in any order. So this expression here will give you another float 4. You can also assign to them, which I think is kind of cool. So that allows you to quickly swizzle, I guess that's the word, these vectors. And if you want to write a literal, as in construct a float, a vector data type from individual scales, that's how it's done. Now, why are those things cool? Let me cover what else you can do with them. Because, you can do all the element-wise operations. So here's another part where the sine and cosine and all of those functions being generic comes in handy, because you can handle a vector just as much as you can handle a scalar. And you can load and store from a float n from a float array as long as that's double line. And there are special geometric functions for that distance. And what all of this means is you have the same way of talking to SSE intrinsics on the CPU. That's not, that doesn't start with underscore and all kinds of weird things that you would really rather not learn about. And in that function, it's kind of cool. It's possibly less useful on NVIDIA GPUs because they're not vector hardware. But since OpenCL tries to be generic across compute devices, it makes sense to have both this form of explicit SIMD as well as CUDA's form of implicit SIMD integrated into the standard. And that's precisely the purpose that these vector data types serve. Then, next, I said that there's stuff for synchronization in the device language. Questions about vector data types?
Right.
Yeah.
Both ways are correct. It doesn't make it harder to write code or that's what I really hate about when writing intrinsics and then go back and write the explicit form. Why don't they just make it the right way?
But the question is, why have both? Why should we have both explicit and implicit SIMD in the standard? Well, obviously to some extent they're reducible to each other. Yet there are strange kinds of hardware that have both explicit and implicit SIMD. That's the case on the AMD hardware, for example. So you have implicit SIMD across a bunch of work items. And then each individual one is 4 or 5 wide. And this exposes that to you. That said, there's a switch somewhere where you can have the compiler try to expose, specified in the standard, where you can have the compiler try to expose the previously explicit part implicit. But there you don't get as many guarantees of what gets in at the same time. Does that answer your question? It's good to have, in my opinion, it's good to have in the standard. Usually you can ignore it if you're on a scale of. But on the other hand, like if you're programming a CPU, there is a promise that vectorizing compilers would do all this stuff for you. That promise, in my opinion, has been standing for going on a decade, if not more. And while the compiler guys catch up, I'll gladly do that. That's simple that might be. Okay. Anyway, sort of running out of time, so I'll breeze past synchronization. We've seen that between host and device there is command keys and events to synchronize. Between groups, between work groups, you synchronize by kernel launches, and then within a kernel, you can have barriers and memory fences. Where a barrier, as golden rule, you learn that elsewhere. But the result, maybe it's useful to quickly state that the results of an algorithm must be independent of the order in which the work groups are. Just think about that. If you want to synchronize within a work group, you have a barrier. Barrier means everybody runs up to it, and then everybody stops, and then everybody gets there. Continue. What's a memory fence? Kind of lower level. A command that you submit to the memory controller that says all the memory operations that I submitted up to here must be complete before you do any of the stuff below here. So it prevents reordering from these two guys are racing. This guy might have pushed to the right, but the read completes before the right, and that's kind of a bad thing. And that's probably not how the memory is. Sometimes you also don't need to explicitly synchronize, where you can use atomic operations. Have you learned about atomics elsewhere? I'm running out of time. The quick story is that at each of the stages where, say, you would increment the variable, between the read where you bring the data on chip, and between the increment and the write, that will be interruptible, and an atomic operation makes that uninterruptible, and thereby you can use that to also collaborate between workers. One particular operation that you might want to look at is this compare and swap. That allows you to do arbitrary complicated things that fit into 32-bit or 64-bit with atomic. So look at the documentation. It's a little bit too much to explain right now. So I'll push the OpenCL implementation stuff to next time. Last thing I want to talk about today is OpenCL is extensible. So just like maybe some of you might be aware, OpenGL, the graphics language, allows extensions. OpenCL also allows vendor and official extensions that add functionality. And you enable that simply by checking for a macro in the header, and by checking in device class extensions for support. And you enable it in the device language by saying pragma, OpenCL extension, whatever you enable. Important extension to have, double precision number. All right. With that, I think we're done for now. Thank you very much. See you next time. Oh, are there questions? Yeah, you have.
Is everything you discussed today provided by OpenCL, like or?
Yeah, all of what I talked about is in the standard, and then there are device-specific things that are exposed exactly as these. Whoops.
Nothing is provided by
at the very lowest level, PyOpenCL just wraps all this stuff and makes it available. And then we'll get to some of the things that PyOpenCL adds to the equation next. Right, and if there's other stuff that's available on specific devices, those will be vendor extensions. Any more questions?